So I hope you got a good fresh rest so that you can start again for 45 minutes. So in the results, some of the results, so these are all the documents. And the idea is that in the documents that you get back from the system, some of them you are going to find relevant to you based on your information need. And some others you are going to not find relevant. Right? And this is again, because as I said, the query itself will only return to you the exact results based on the Boolean system. However, the way you write the query might be ambiguous with what you had in mind. For example, if you look for information on ETH and you type ETH, then you're going to have a lot of ETH Zurich pages, but maybe you're going to also have information on the Ethereum blockchain, right? So these will not be relevant to you. The query returns them, but it wasn't what you were looking for. So this is why we classify the return results. This is everything returned by the system as relevant to you or not relevant to you. These are called also the true positives and the false positives. True positives, these are all positives because returned. True because they are returned to you and they should be returned to you. False positives because these are returned to you, but they shouldn't have been returned to you because you don't care about this. So this is what is called false positives. So the first thing we can already compute with the number of items, right here in green and the number of documents in red is the precision. So the precision is the number of true positives divided by the total number of positives. So it's everything that you get and should get divided by everything you got, right? So it's the ratio of what is relevant to you in what you got. So the true positives divided by the returned. What is the precision there in here? What is it? If I compute the precision, if I have exactly 8 documents right there that are true positives and 8 that are false positives, what's my precision?
So there's an answer in class, half.
Yeah, half. And in the chat?
50%.
Yeah, which is equivalent. Yes, absolutely. This is 8 divided by 16. So this is indeed 50%. What's the precision here?
There's an answer in class 1.
Yes, absolutely. So 1 is the same as 100%, right? So this is why you can either say 1 or you can say 100%. That's the same. All right. So yes, indeed, this is 100%. This is 1. What about here? What's the precision?
0.
Exactly. So here you're really out of luck. Like everything that you got from the system is just something you don't care about. Here you were really lucky because all you got was actually relevant to you. Right? So you see 100% is great. 0% is not great at all. All right. What's the precision here?
So 80%.
Yep, correct. 8 divided by 10, 80%. All right, very good. All right, let's add more. So here I said this is what's returned to you, but there are also documents that there were in the collection that you didn't get as a result of your query, right? So I put them here. These are the negatives. These are the negatives because they are there, but you didn't get them. So I put in there the relevant negatives. Is it good or is it bad? These are documents that are relevant to you and that were not returned to you. Is it good or is it bad?
So bad.
It's bad, exactly. Here, these are the documents that are irrelevant to you and not returned to you, so this is good, right? So we like what there is in here, we like what there is in there, we don't like this, we don't like this, right? So this is the idea. These are the true positives and the true negatives, these are the false positives, and these are the false negatives. All right. So there is another one that we, quantity that we love to compute, which is called the recall. The recall is a bit different from the precision, right? So for the recall, you still take the relevant, so the true positives, but what you divide it with, instead of going to the right with the returned irrelevant documents, you go below to the non-returned relevant documents. So this is what you should have gotten, but you didn't. So the system failed to give you these documents. So the recall is this divided by that, right? What's the recall here? That should be instant. The recall is
half
50%. Basically, you should have gotten all of that. You should have received these 16 documents, but you only received 8. So it only recalled 50% of the documents, right? So the true positives divided by what is relevant. All right. This is 100% because here you were extremely lucky. You basically got everything, right? You might have also gotten a few irrelevant ones, but at least there is nothing there. You didn't have any false negatives, right? Here, the recall is 0%. Here, it's really a catastrophe. So basically, you took the time to write down your query and so on, and in what you received, there is absolutely nothing relevant to you. Everything was basically there that you received. It's the irrelevant documents. So you're out of luck if your recall is 0%. All right, and here is 67% because 2/3 of the documents are returned in there, right? So you are relatively lucky, but you still have a few that you didn't get. All right, so precision and recall. So there is now this type 1 error, type 2 error. I'm going to be honest with you, I never remember which is which between type 1 and type 2, but I think it's important, and especially because this is also used in machine learning. So maybe some of you are also taking a machine learning lecture, and in machine learning, we also like to say type 1 error and type 2 error. So a type 1 error is basically when you have a false positive. So you basically return something you shouldn't, or you basically label something. For example, you have a picture, you say this is a cat. No, it wasn't a cat. So this is a type 1 error. A type 2 error is when you get a picture, it's a picture of a cat, but you labeled it with something else than a cat. That's a type 2 error, it's a false negative, right? So yeah, so this is the link with machine learning, because in machine learning, I mean, the best example I'm aware of in machine learning is that you get millions of pictures and you're supposed to say this is a cat or this is a dog. And somehow with deep learning, we are really good at doing these things today. Do you have a question?
Yes. So how do we consider the fact that these documents may be of totally different size when calculating these percentages?
That's a good question. So we are coming back to the definition of documents. And when we compute here the results, we really do not care about the sizes. Maybe this is a very small document, maybe this is a very large one. We still count it as one and as one, right? So typically, we really count the number of documents when we compute precision and recall, right? If that doesn't work, then maybe somebody would like to change the definition of precision and recall and say, okay, now we have the weights. We basically weight the documents with their size. That's one way of doing that. Another way is to change the definition of a document, because maybe if you realize that in your repository, you have very small and very large documents, then what you could do is to split the very large documents into smaller ones, right? This is one way that you could do it, right? But in the core definition, we really just count documents, and this is just an integer. It's the number of documents in each one of these 4 categories. Did I answer your question? Yeah, all right. Please do not hesitate to ask questions, right? I really want to encourage you to do that. This is an interactive lecture. This is what I'm here for. I'm basically here in order to help you learn and make sure to answer all of your questions. Never forget that maybe you need to break the ice, right? But maybe some of you are shy or do not dare to ask a question, or maybe you're thinking, okay, that's a stupid question. There is no such thing as a stupid question. And if you ask a question, it's very likely many other people have it. So really never hesitate to ask. Okay, so what does this look like if there's high precision? So high precision means that whenever I return things to you, this is usually relevant to you, right? So it means we don't have much here. This is high precision. It still means that I might not return everything I should, right? I might still be missing a lot of relevant documents, but at least I'm not inundating you with garbage. That's basically what's happening. I don't have much in there. So this is a high precision system when that part is almost empty. This is a high recall system, right? It means that I'm basically returning to you almost everything that I should be returning to you. Maybe it's going to be completely drowning in garbage because I'm also returning all of that, but at least there is almost everything, right? I didn't miss anything that I was supposed to return to. So, right, so high precision and high recall, right? So this is how it would be. And as you can imagine, it's very, very complicated to have both. So typically you're somewhere in between, right? So either you have high recall or you have high precision, but not both. And basically when you design a system, you just basically need to tune it and say where you want to be. Are you scared of false positives, or are you scared of false negatives, right? And this is how you adjust the parameter of your system in order to make it work for you. And this really depends. There is not really a generic answer to that. This really depends on your use case, right? In some cases, false negatives are not a problem. In some other cases, false positives are not a problem. So, but what I can tell you is that very high precision and very high recall are very, very tricky to get in practice. All right. This closes the part on precision and recall. I will come back to that in a few weeks in the semester, probably in May or something, end of April, May. I'm going to have an entire chapter on evaluation, an entire lecture on evaluation. I'm going to show that there's not just precision and recall, there's others as well that you can compute and all ways of evaluating an information retrieval system. Right? But this is just a start. I just give you the appetizer with just precision and recall, and now you know what precision is and you know what recall is. And so I assume that you're able to compute that now if I give you numbers. All right, any questions so far before I move on to the next part? We don't have any questions? All right, let's move on then to inverted indices. That word should be familiar from the relational database systems lecture, right? I think it's Zurich who is teaching it at the moment. All right, so I'm assuming that that most of you actually had this lecture. So this word, as I said in the index, is familiar to you. That, of course, wasn't an index, right? It was just some structure, some matrix structure that we call the incidence matrix. But I told you that's in order to fit on a slide, I picked 10 documents and 6 terms. In reality, as you might imagine, that's quite different. So for example, you might, well, if you try to index the Library of Congress, or I don't know, the web or Wikipedia, you might find that the number of terms is closer to, let's say, 500,000 in a corpus, right? So it's much more, that wouldn't have fitted on my slide if I had shown you 500,000 of them, right? But typically it's 500,000 terms in a very big or large corpus. For the documents, well, typically 1 million. If you're looking at, let's say, a typical library, big university library, you can easily have 1 million documents, right? I actually don't know how many books there are at ETH. That would be interesting. I should look it up, how many books they have in the ETH library. I just know that it's so many that they need these little robots that bring it to you. So basically book it in the system, and then you have these robots on wheels that bring the books, and then you get a small message when it's there, and you can go get it, right? But anyway, it can very easily be 1 million of documents. So we are looking at a matrix that has 1 million columns and 500,000 rows. So we are looking at 500 billion Booleans, 500 billion Booleans. So this is roughly a bit less than 1 gigabyte if you do the math, right? So each Boolean is a bit. If you want a byte, you divide by 8. So this is a bit less than one gigabyte of memory. So it fits on your disk. Of course, you could still store that on your laptop, but nevertheless, this is actually quite large, right? But my question is, how many zeros do we have in there, right? How many zeros are we going to find in there, and how many ones? And the idea is that typically, if you assume that a document typically has 1,000 terms, so we basically cut the documents or picked the size of the documents in such a way that they have 1,000 distinct terms. We are still in the set of term semantics. So there is here 1,000 ones, and the rest are zeros. So in total, if you do the math, there's going to be 1 billion ones. How did I get that? I multiplied the 1,000 right there with a million right there. So there's a million documents, and in each one of these million documents, there is 1,000 terms, so it means 1,000 ones. So we have 1 billion ones in there. And that means that we have 499 billion zeros. That's a lot of zeros. That's an enormous number of zeros. In fact, it's an enormous waste of space because we have less than 1% of the space that's actually marked with a 1 right there. So if I even compute that, it's 99.8% empty. So that's a huge waste of space to do it this way. And let me tell you, this is why we do not do it in this way. In practice, we have ways to do this more efficiently. This is what we call very space inefficient, but nevertheless, at least in theory, that's a representation like any other. At least for mathematicians, in mathematics, we don't care about spatial efficiency, right? But if you want to implement a system, you do. So can we store that in a better way than this, that would also scale to billions of digits? This is the question that I'm now asking you. All right, now you can answer this question. How do we solve the 99% plus sparsity issue? That's called sparsity. We have a sparse matrix. Are we going to rent a cluster of machines on Amazon and hope the ETH finance and controlling department doesn't complain with us? Or do we list only the terms used by each document rather than mark all terms with zeros and ones? Or do we list only the documents containing each term rather than mark all documents with zeros and ones? Or only Google knows, and you have an ADA, so you cannot tell us. So there are two competing answers that have a small majority. So do we list only the terms for each document, or do we list only the documents containing each term? What do you think? Do you want to change your opinion? Do you want to rally the majority? Do you think the minority is actually correct in that case? What do you think? Have a chance to change your answer. Let's see if it starts converging to 100% or not. Oh, seems like you're sticking to your decision. All right, so turns out that we list the documents containing each term. Why is that? Why not the terms used in each document? Is there any reason?
Sorry, can you repeat that? There are far fewer documents than terms.
Let me think. When you say fewer documents than terms, do you mean fewer documents per term than term per documents?
So I think in general, there is fewer documents than.
And terms, yeah. So I'm not sure. In the slide before, we had, I think we had a million documents and 500,000 terms, right? So the number of documents was, I think a bit bigger. But maybe I misunderstood what you actually mean here.
So there's also some on the chat.
Yeah. Mm-hmm.
So more likely we want documents containing the term X, not all terms of document Y. So tailored to the common query.
Yes, I think that's pretty much the idea, exactly. So think of what you want to use this for. You want to use it in order to answer queries. So you're going to have the terms and you're asking for the documents. So this is why you want your index structure to give you the documents if you ask for the terms. This is the direction in which you want to go. In fact, if you look at the other answer, you list the terms by each document. What you are looking at is not the index, it's actually the original collection. If you have plenty of documents and for each document you have the terms, you're looking at the book, right? Or maybe you're not looking at the book, but you're looking at the shuffled book after you did the duplicate elimination and forgot the order. But you're pretty much looking at the original, right? And in fact, the fact that we list the documents containing each term by term, is the reason why we call it an inverted index. It's an inverted index. If we were listing the terms for each document, that would not be inverted, right? And the notion of inverting, in fact, also in relational database management systems, is the added value of the index. You basically invert everything, but this is all pre-processing that you do just once. And since you have inverted everything at query time, when the query arrives, then you are super fast because the inversion was already done before. Did I make sense? Did it make sense to you? So I think you have the right intuition. I think the arguments that you made earlier about the number of terms and the number of documents probably plays a role as well when you start building the structure. In fact, we will come back to when we look at the sizes. If you start having a lot of documents and a lot of terms, I have an entire week dedicated to that, on how we manage to actually scale it up. We are not going to go as far as to rent a cluster on Amazon, but you would be able to do that, basically. If you want to do it, then you will learn that in the lecture, how you do that, right? But then I will let you deal with the finance and controlling, not me. All right. I'm coming back to the slides. Just want to make sure that I land exactly at the right position. Yeah, so that's this one. All right, very good. So that's good. You're participating. That's really nice. And feel free to ask questions and so on. And feel free also to answer my question. Maybe the answer is correct. Maybe it's incorrect. Maybe it's half correct. But it's the whole point of teaching, right? And this is how we learn together, right? So never be afraid of making mistakes. By the way, that's called, actually, I don't know if you heard of Manu Kapoor's work. He's a professor at ETH about productive failure. A great way of learning is to make mistakes. This is how you make progress. All right. So can we store it in a better way? The answer is yes. So here you notice that if I got rid of all the zeros that are in there and only checked the ones in there, what we can do is for every term, list the documents. So here we have 1, 4, 9, and 10. So I put 1, 4, 9, and 10. Then let's forget about the structure and just have the listed documents. What happened here? There is nothing magic that happened. I just got rid of the zeros. So instead of having ones and zeros, I really take the actual numbers, 1, 4, 9, 10, and I really actually store the number 1, the number 4, the number 9, and the number 10. Right? This is what we actually do. And you see this takes much less space now than before, because all the space that was wasted with zeros is now gone. Of course, the ones take more space because now I just don't store ones. I actually store integers. So instead of a single bit, now I have maybe 32 bits if I use 32 bits for this, right? But just so you see, we still saved a lot of space in there. All right, and you see, if I ask you queries, like if I ask you, okay, what's the result of a query, I don't know, T and X, what's the answer to query T and X? What does it return me? Pretty sure you'll be fast doing that. T and X, which documents?
1 and 4.
1 and 4, exactly. See, 1 and 4 in there and 1 and 4 in there. All right, very good. Now, a bit of terminology. This here, that part here where we have the terms, it's called several things. It's called vocabulary and dictionary. There's a subtle difference between the two. The vocabulary is, if you look at the set of terms, this is the vocabulary. When we call it dictionary, we implicitly assume that there is some search structure. What kind of search structure could you imagine? You've learned that normally in other courses. How could you have a search structure in there? Some data structure that allows you to efficiently find terms. Any idea? All right, so I'm not going to tell you. I'm going to keep it for, I think, either next week or the week after that. So I'm going to come back to that. There will be some structure in there. And it is usually when we have this structure that allows for an efficient lookup that we call it a dictionary. I see on the chat, correct answer.
A binary search tree.
Yes, exactly. This is one way of doing that. So when you have, let's say, a binary search tree in there, then this is what you would call the dictionary, right? It's the actual structure that makes you look it up. And vocabulary would be if you just look at the terms themselves as a set. All right, this here is called a posting. A posting is a term document pair. It means term U appears in document 6. This is what is meant here. Term U appears in document 6. That's called the posting. And we assume that each document has a document ID, also called doc ID, and we just put the document ID in there. We could have said 5U, 6U, 7U, right? But why are we going to waste the space? It's all U anyway. So this is why we just put the U once here, and then we just put the doc IDs. Okay, so this is a posting. This is a postings list, a list of postings, right? So this is called the postings list. So what we have in this inverted index is that every term is associated with a postings list, and this postings list tells you which documents that term belongs to, right? And the postings as a whole, this is all of that. So you have the vocabulary or the dictionary here, and you have the postings right there, organized as postings lists. All right, and this is called the index. Right? And if I give you the complete name, it's going to be called standard inverted index for reasons that I will come back to. Inverted, I can already tell you. Inverted is what I said about listing the documents per term and not the terms per document, kind of inverted it. All right. There's something else we do typically when we create the standard inverted index. What we love to do as well is count the length of the list. So here we have 4 documents. So we put a 4. Here we have 3, we have 5, 1, 4, 3. So we put the counts of each postings list. It's the number of documents that contain the terms. And that way we can see the most frequent terms. Here we see that term V is very frequent. It appears in 5 documents. It's actually the most frequent term.
This is something you can see. Yeah, question in the class. Yes.
About the definition from before, are the postings same as the index?
So the question is, are the postings the same as index? Is it a synonym?
Not exactly. So what I call index is the entire thing. The entire thing, the entire structure is called an index. Right? What I call postings is really just that part in here, right? Without the terms. It's really just the postings. In the singular, it's just one of these. And in the plural, it's all of them, right? And if you say postings lists, then you really just mean one of the rows here, one of the lists, right? So posting in the singular, postings list, and postings as a whole, but it doesn't contain the term when you say postings, right? At least in the physical structure, it doesn't contain them. All right?
Yes.
Perfect. All right, I'm trying to be precise with you. Of course, the conventions can vary, but this is my understanding. So vocabulary when it's flat, dictionary when there is a binary search tree or equivalent, postings lists, postings, and index. All right. Okay, so let's build one together then. Let's do it. So I have an example. 4 documents. Let's not take a million. Let's not take a million of them. Let's just take 4 of them. So we have 4 documents. They are here, document 1, 2, 3, and 4. This is probably Shakespeare or something. I'm not actually sure where that comes from, but probably something like Shakespeare. All right. So what do we do first? We tokenize. What does it mean to tokenize? We just look for the spaces and cut the spaces. This is typically what we get after tokenizes, right? Tokenizing. We just, every time there is a space, we just separate, and what we get are tokens, right? And the tokens are the little rectangles there. Everyone is a token. All right. I'm going to make simplifying assumptions today. I'm assuming I just look at spaces. In reality, it's much more complex than that, and I'll have an entire week for you in order to explain to you how actually difficult that is. But just for today, we just look at spaces. All right. So then let's reassemble everything. So here by color. So I basically take the yellow, green, yellow, red, blue, and green, and then I'll just put them in that way, right? So all I did is just rotate. Okay, transpose. Then I assign the document ID. So basically, this was document 1, this was document 2. So I just say every time this is document 1, 1, 1, 1, 1. These ones that was document 2, 2, 2, 2, 2. This is document 3, 3, 3, 3, 3, and 4, 4, 4, 4, 4. Right? So I just assign the document IDs. I actually took the same that I had right there. Okay. What do I do next? Next, well, let's sort alphabetically all these terms, right? Let's sort it alphabetically. This is what we get. A, B, C, F, H. So you see it's all alphabetically sorted. But of course, now it's shuffled with the document IDs, right? But we don't care. We want the alphabetical sorting. What's next? Let's merge. You see, COM1, COM4, COM3. These are pairs of term documents. This is actually a logical posting, if you want. These are logical postings. So we have here the occurrence of COM in 1, in 4, and in 3. Let's merge them. So now I have COM in 1, 3, and 4. So I just merge these 3 to this, and now I have this list of document IDs. Right. So what we did is we went from the logical postings. On the logical level, these are pairs of terms and documents, but since it's the same term, on the physical level, I only keep the document IDs for the same term. So this is why I save space by only storing the term once and only have the document IDs there. All right. And then I just add some structure. So of course, I said a list. So let's use the linked list, right? So we have a linked list in there and everywhere. And now I have this alphabetical sorting. I didn't put a binary search tree there because I don't want to talk about it yet. So right now I'm just saying, okay, this is sorted alphabetically and that's it, right? But later we'll come back to the structure. All right. And now, as I said, we also like to compute the counts, right? For example, here there are 3 documents. So 3 documents that contain COM. So I put a 3 right there and I put them in purple right there, right? So these are called the document frequencies. And I'll come back to the concept of document frequency, term frequency, and so on. This will be in a few weeks from now. For now, you can just consider that this is the length of the list that we put there. All right, do we have a question?
Yes. Say we had R and Rs. Would those map to the same token or not? I think it's just plural.
That's a very, very good question. And this is why I was very careful when I did this tokenizing here. I said, today, just to keep things simple, I'm just looking at spaces. I'm just looking at the spaces and I cut whenever there is a space and that's it. So if I say our and ours, it's not the same just because I only looked at the spaces. But you're absolutely correct that in practice, you do actually want to merge our and ours, right? But again, this will be in another week, right? I cannot cover everything today, but you're asking exactly the right question. This is absolutely something that has to be considered in a system. And it's part of what is called here the linguistic pre-processing. This is when you are going to look at plural, singular, and so on and so on. I'm going to spend an entire week pretty much showing you how complicated that is. And if at the end you are exhausted because this was so complicated, then I made my point that it's very complicated. All right, but you'll have the basics of how this is done. Right. All right, but I'll be careful not to exhaust you too much, just to scratch the surface of that. All right. Anything else? Any other questions? None? All right, so this is what we get. We get, oh no, we even added the document frequency, so here we go. So now if we look for something, let's say we look for this word, this is the query, then we use the alphabetical sorting, so we can pretty much look it up. Here it is H, hour. There you go, and then you can see, oh, there's 3 documents, document 1, 2, and 3, and as a consequence, you can return documents 1, 2, and 3. So typically, if you want to be user-friendly, when you have implemented this thing, you don't throw 1, 2, and 3 at the user. Typically, you're nice and you retrieve document 1 and you print it like this, and typically you even look for the word, put it in bold, you know, to even show that it was there, or maybe some yellow overline or something like that, right? So this would be the user-friendly presentation at the end, right? So documents 1, 2, and 3, 1, 2, and 3, right? All right. Now, how do we do the conjunctive query? It's not going to be a bitwise end, right? Because we no longer have the matrix, we got rid of it. Now we have the standard inverted index. How I am doing a conjunctive query? Well, first I need to look up the 2 words, hour, com, here they are, right? Hour and com. So I need to find the documents that are both in here and in here. What's the complexity of that? What algorithmic complexity do you think we can achieve here? What complexity is it going to take? If I call n the typical size of a list, is it going to be exponential, logarithmic, quadratic, linear?
Linear.
Yes, that is correct. It's even the optimized answer. Why linear?
So because they're already sorted, and we can have like 2 pointers and increment them as we compare.
Absolutely, exactly. It's because it's pre-sorted. If it had not been pre-sorted, that would have been quadratic, right, by default. All right, actually, even if it's not sorted, you could still do it in a linear way, but here I refer to the implementation of joins in relational database management system, but I'm not going to go into that. So since it is sorted, indeed, you're absolutely correct. This is going to be linear. So here we just scan left to right, 1, 3, 1, 3, and we get 1 and 3. All right. So you see at the end, you have document 1 with com and hour, and document 3 with hour and com. So this is all good. And you see the order doesn't matter. Right? It's just a set of words semantics. Do I still have time? Well, I have a few minutes left. Do we have a question in chat?
Isn't it n log n when it is not sorted?
N log n or n, let me think. So if I think out loud, what you typically do is use a hash table. That's how you implement a join. So you basically traverse the first one and store everything in a hash table. And then you go over the second one and you go again linearly over it and then look up in the hash table. And every time it's n. So I think, but again, maybe I'm making a mistake because this is live and maybe I'm not thinking right. So I think it's linear, but with an enormous constant. That's basically what I think it is. N log n would be if you sort something, but actually we don't need to sort. We don't need to sort because we just want to return the intersection, right? So we don't have any particular order. Do you agree, or maybe you want to challenge what I'm saying? Maybe it's actually n log n, and I'm just not thinking correctly. That's also entirely possible, right? So if you think I'm making a mistake, send an email, and then we discuss it, and then I'll discuss it again next week, right? Did I convince you? Let me ask it that way. Did I convince you that it can be done in a linear way with a large constant? Or did I not manage to convince you? On quiz. Okay, wonderful. And by the way, what I see in the chat, maybe you can read what is written in the chat, the previous ones, because these are excellent points. Let's take time for that.
Couldn't you sort it in n log n and then queries?
Absolutely. And you could do it in, and then you would get n log n. So you basically say, okay, let me sort the two lists, n log n, and then you use this intersection algorithm that I'm going to show to you. So this is good. By the way, linear is not necessarily better than n log n, because again, the constant can make the difference. So if you have something linear with an enormous constant, and you have something n log n, but the constant is smaller, sometimes n log n is actually not so bad, right? Oh, maybe I misunderstood the question. Can you maybe read, Abhishek?
Yes, so I was thinking the cost of searching in the unsorted case would be order of n log n and not n square.
Yeah, so let me rephrase it as n squared would be an extremely inefficient and naive implementation. I would put it that way. It would be the case that you look at all the pairs from the two lists. And that would be very highly inefficient. That I give you. This would be extremely inefficient. And if you directly come up with an n log n implementation, you're already better than I am for the first naive implementation. Yeah. Very good. That's a good conversation. Very good. So your thinking is exactly the right way. That's perfect. Do we still have time? Yeah, I probably have the time. Oh, this is the conjunctive one. So for the conjunctive, it's the same thing. You take the two, and then you just do the union instead of the intersection. So if you do this or this, then you have 1, 2, 3, 4, right? And then you output. But what I wanted to show you is just the animation. I'm going to finish on that. The animation of this algorithm, when you said, okay, we can do it in linear time because it's already sorted, this is what happens. We start indeed with 2 pointers right there. If they match, we copy over the matching number. If they do not match, we just increment the smaller one and keep the larger one where it is. So here it doesn't match. Now we increment the smaller one, doesn't match, it matches. We copy over the 4. Here we have the 5 doesn't match, so we increment it. Here the smaller one doesn't match, 7 doesn't match, 8, 8, we have a match, copy it over. 9 doesn't match, we increment. 10, 11, we increment always the smaller one. Now it's 11, the smaller. 12, it's a match. And there we go, it's the end. That's the intersection algorithm. And you can see it's linear. And the constant is actually much more acceptable than the other one with the hash that you would need if you didn't sort them. All right, so I hope you learned something today. I hope that it was understandable. Let me finish just by actually checking that you understood what I was telling you. And based on that, I can accelerate or I can slow down just to make sure that everybody's following. So tell me, and then you're going to be free for the exercise session. That is excellent. So half of you understood everything and everybody is above 80%. That's wonderful. So that's a great start. So now you are basically in a position to implement that. And actually in the exercise next week, you are going to start implementing. So thank you very much for attending, everybody. Thank you, Abhishek, for moderating. Enjoy the exercise session and see you next week. Thank you very much. Goodbye.
Thanks.